Hello friends, now we will start with the next topic of power amplifiers, that is transformer coupled class A amplifier. We have already discussed in the previous topic, that is class A amplifier with direct coupled load. The efficiency of the power amplifier with direct coupled load is just 25% maximum. So if you want to improve the efficiency, we go for the coupling of load with the amplifier through a transformer. So that amplifier is known as transformer coupled class A power amplifier. So let us see the circuit. This is the circuit diagram of class A amplifier with transformer coupling. This is here. This is the load resistance which is connected to the amplifier through this transformer. This is the transformer having turns ratio, that is 1:n. If you take it in terms of primary and secondary, so on this side it is N1, on this side it is N2. That is how it have, right? And of course this is the biasing arrangement. So this is the amplifier with transformer coupling. In this case, the interesting part is when we apply AC signal, so the transformer primary has two types of signals. One is DC current coming from VCC, and second because of the AC input signal. So the primary will have two components of the current, that is AC current and DC current. So in this is what? This is primary coil of the transformer. So in primary winding of the transformer, when DC current flows, the resistance offered by a coil, by an inductor, by the primary winding, the resistance offered is 0. When resistance offered is 0, this VCC will come directly at this point. So voltage VC will be equal to VCC. And if you neglect drop across this, so VCE will be equal to VCC here. So that is important point. In case of transformer coupling, there are no losses in the primary winding because its resistance is low. Therefore, efficiency of the transformer coupled amplifier is more. If you see the characteristic of the class A amplifier, these are the characteristics. Here, you know, these are the characteristics of the BJT. This line is known as AC load line. You can see on biasing of BJT the meaning of AC load line. This line, we know the voltage VCE is approximately equal to VCC. Therefore, the voltage VCE is not affected by the collector current, and it is equal to VCC. And the intersection of this line, that is load line, with the characteristic of BJT, this is base current, which is base current at Q point, and this intersection is known as Q point. Fine. So the interesting point here is, you should remember the voltage VCE is equal to VCEQ. The voltage VCE at Q point is equal to VCC. This gives you the variation. Now, if your DC current, the DC input current, maybe it is like this, varying like this from here to here between these two limits, corresponding variation in voltage VCE is like this, corresponding variation in collector current is like this. Why? Because your Q point is lying in the linear region, and your collector current is proportional to base current in the linear region of the characteristic. So now we will see the expression for the conversion efficiency, right? So let us see, we have to find transfer of the load impedance, input power, output power, and conversion efficiency. What is the meaning of transfer of load impedance? This load connected here can be transferred to primary side. So load seen on primary side can be taken like this. Say current in this is what? I1. Current in this is what? I2, right? This is I2, right? So the ratio, transformer ratio of a transformer, you can take it like this. I1 by I2, or rather than taking like that is current I1 by I2 is equal to the transformation ratio N2 by N1, which is N2 by N1 will be what? That is equal to N. Similarly, voltage transformation ratio V2 by V1 is equal to N1 by N2. This is the general expression of transformation ratio of a transformer, which is equal to 1 by N, right? Now if you divide, say this is equation 1, this is equation 2. If you divide 2 by 1, we have, so if you divide 2 by equation 1, we will be having V1 upon I1 equal to V2 upon I2, and that will be equal to 1 by N square. Now V2 upon I2, this is secondary voltage V2, this is primary voltage V1. So V2 upon I2, this is resistance this is current I2. So V2 upon I2 is equal to load resistance. This is RL is equal to what? V2 upon I2. So this can be written like this: V1 upon I1 is equal to 1 by N2, not N2, 1 by N square. It's not N2, it's N square. This is N square. This is N square, right? So this will into what? V2 upon I2. This will be equal to 1 by N square multiplied by load resistance RL. And this ratio of V1 upon I1 is nothing but impedance resistance seen by primary side, and this is equal to RL dash. RL dash is known as the load impedance or load resistance referred to primary side of the transformer. So when you see this is equivalent to the resistance connected at this side, primary side, but that is the load resistance RL dash is in respect to AC signals. This ratio is in respect to AC signal, AC I1, AC I2, AC V1, AC V2, not for DC. For DC, the resistance offered is 0. For AC, the resistance offered by this winding is RL dash, which is nothing but 1 by N square into RL. That is known as transformation of the impedance, right? So you should remember this. This is important. You can have question in exam, right? So then we will see, this was the transfer of load impedance. Then input power. When you say input power, then DC input power. So the DC input power, P input DC is equal to VCC into ICQ, right? Or that's collector current at, that is DC collector current, you can say, right? ICQ. And you know what is VCC? VCC here in this case is nothing but that is equal to VCQ into IC, right? ICQ. That is what you can say. Now, this is the DC input power, DC power, right? Now let us see the AC output power, AC output power. But remember, we will be talking about the AC output power on the primary side of the transformer, and you can transfer it to secondary side, right? Basically, power on the primary side will be same as power on the secondary side, neglecting losses. Fine? Because transformer changes the voltage and current level, not the power level. Power on the primary side will be same as power on the secondary side. So if you take, see carefully, I'll go back, see your voltage VCE and current IC. This is output voltage of the BJT or amplifier. This is output current of the amplifier. So product of these two signals will be giving you the power. So voltage VC is AC voltage current IC is AC. So in terms of AC values, peak value of this current is what? That is IM. Peak value of this voltage is how much? That is Vm. So I can say, if you find the AC output power, so that will be PAC out will be equal to Vm, or rather than saying Vm, that is Vrms, into IRMS. This is VCE RMS, you can say, and that is equal to Vm by root 2 multiplied by Im by root 2. That is equal to Vm into Im by 2. Now we know Vm. Please see the diagram again. Vm is this. So this voltage is what? VCE maximum minus VE minimum, that divided by 2. Similarly, IC maximum by IC minimum divided by 2. Right? So you can write, that is Vm is VCE maximum value minus VCE minimum value divided by 2, right? Similarly, peak current Im will be equal to IC maximum minus IC minimum by 2, right? Or I can put these values here. So you got PC AC output power will be equal to VCE min minus VCE, or this is max, VCE min by 2 multiplied by IC min, IC max minus IC min by 2 Vm Im by 2. So this becomes multiplied by 2. Or you can simply, modify this equation, or you can write it like this. Put it in bracket, and complete denominator can be replaced by how much value? That is 8. That's it. Fine. That is the AC power output, right? Now if you talk about conversion efficiency of transformer coupled amplifier, so that will be P AC out by P DC input, right? So Pi DC. So you can write that Pi DC, Pi DC. So this gives, you can write either this or this, this expression or this expression, it's your choice. So just to make it smaller, I will write Vm Im by VCE cube, or I can say VCC, I can write VCC as well, VCC ICQ, right? So, or you can further write, you can write this expression completely here, VCE max minus VCE min divided by how much? 8 into IC max minus IC min, right, divided by 8 VCC into ICQ. You can write it like this, or you can make different expressions for this depending upon values given to you, right? So this is ICQ, Fine. Now, if you have to find maximum value, in that case, how to proceed? Please see carefully. We know here what is VCC. VCC is equal to VCEQ, right? VCC is equal to VCCQ, or you can say here, I will write it like this. Let VCE max is equal to VCE maximum is equal to twice VCQ, twice VCC. Why so? Please see it carefully. And we will assume that VCE min is equal to 0. I will go back to the diagram. Please see it carefully. If VCE is 0, so this is almost center of this portion, and VCE max will be equal to twice VCC, right? Provided VCE min is 0. So when VCE min is 0, VCE max is equal to twice VCC, right? So similarly, let IC min, minimum IC current is 0. In that case, IC max will be how much? Please see carefully. When IC min is 0, when this is 0, IC max will be equal to twice ICQ. Why? Because it is almost at the center, right? So when IC is 0, IC max will be equal to twice ICQ. So this is twice ICQ, right? So now, in that case, what will be the efficiency? I will write in this portion, right? In that case, the efficiency will be, please see carefully, VC min is 0, VC max is twice VCC. So this is twice VCC. IC min is 0, IC max is twice ICQ, right? Divided by 8 VCC into ICQ, and this ICQ, this is cancelled out, right? So this is ICQ, so this is equal to 1 by 2, and if you take in percent efficiency, that will be 1 by 2 into 100, right? So it will be how much? This will be equal to 100. So efficiency becomes this will be how much multiplied by 100, right? So here, please see carefully, the percentage efficiency becomes how much? Percentage efficiency becomes 50%. So percentage efficiency becomes 50%. That's what I'm trying to say. So the maximum efficiency of class A amplifier with the transformer coupling is 50%. So efficiency has just doubled in comparison to a direct coupled amplifier, but it has got certain disadvantages and advantages. Advantage one, of course, we have seen there is no DC current through the load. The DC current is normally avoided in the load when the load is a loudspeaker. So that becomes advantage, that DC current will not pass through the load such as loudspeaker. Second, the efficiency has doubled, and transformer helps in matching of the load with the output of the transformer by selecting suitable transformation ratio. So there are some advantages of this. Efficiency of the amplifier is doubled. It provides isolation from DC circuit. That is what I have already told. Because of the transformer, the DC biasing current is undesirable in some types of loads such as loudspeaker, and it provides coupling. It provides isolation, in fact, right? And it provides impedance matching between the load and active device and high gain. These are some of the advantages. Let us see disadvantage. Remember, when transformer is connected, so there is a current, DC current passing through the primary of the transformer, and when DC current passes through primary of the transformer, it results into core saturation of the magnetic core of the transformer. And when magnetic core of the transformer gets saturated, it gives harmonics, it gives rise to the harmonics on the output side. So there is possibility of introduction of harmonics on the output side in case of the transformer coupled amplifier. That is one important point to be noted, right? Second point is, the transformer coupled amplifier gives poor low frequency response. The low frequency response is better in direct coupled but poor in case of transformer coupled load, right? So I have already explained, because of the saturation, output voltage of the transformer becomes non-sinusoidal because of the introduction of the harmonics. So the core saturation introduces harmonics in the output of the transformer. Fine, so that is undesirable, and these harmonics can be eliminated by using push-pull. There is an arrangement called push-pull arrangement. That amplifier does not have the problem of core saturation. So push-pull arrangement amplifier does not have the problem of core saturation or problem of additional harmonics in the output of the amplifier, right? So this is your class A amplifier with transformer coupling. Now we will see the examples based on the transformer coupling. There is a simple question here. The question here is, a class A transformer coupled transistor power amplifier is required to deliver a power output of 10 watts. So output output power to be delivered is 10 watt. The maximum power rating of the transistor should not be less than. If it is required to deliver power of 10 watt, efficiency of the class A amplifier with the transformer coupling is how much? 50%. So in that case, if it is efficiency is 50%, if output is 10 watts, we know the efficiency of amplifier is what? That is output power by input power into 100, right? So the efficiency of this type of transformer is 50. Class A amplifier with transformer coupling is 50%. So P out by P in into 100, or that gives P input equal to how much? 2 multiplied by P out. So P out is how much? That is given to you. That is 10 watt. So this is 20. How much? 20 watt. The input power of the transformer is going to be 20 watt. So the maximum power rating of transistor should not be less than 20 watt because of the requirement of 10 watt of the output power. So this is your answer. Fine. That was question in electronics in GATE 94. Fine. So there can be that type of question, but there are a lot of questions in PSU exams from power amplifiers or in engineering services as well. Fine. So that finishes your class A amplifier with transformer coupled load. In next video, we will be talking about class A amplifier with push-pull arrangement. So wait for my next video. Thank you very much for watching the video.